Alright, welcome to today's video. Today we're going to be focusing on the AP Calculus question from 1999, the BC exam question number 5. This is a type 4 problem, meaning it involves area and volume, and part A and B can be covered in AB Calculus, and part C is BC specific. So AB students, follow along for the first two parts. Okay, we're given a region R, and it's between the curves y equals x equal e to the x squared and y equals negative 2x, and a vertical line at 1. Part A is to find the area of region R. So let's redraw this here for the sake of discussing the problem. And what we're going to do is sketch in a representative rectangle. And the area of one of the representative rectangles is going to be the height of the rectangle times the width of the rectangle. So for just the one rectangle, the height will be the top curve minus the bottom curve. So that's xe to the x squared minus the bottom curve, negative 2x. And we multiply that by the width. And the width of our rectangle is delta x. And so that is one rectangle. If we start to apply calculus and make this rectangle thinner and thinner and thinner, and add up an infinite number of those rectangles, we get the idea of the definite integral. So the area of all of the region would be the sum of all of our rectangles. Height times a width now of dx, because we've gone to the differential form for that width. And the rectangles stack up along the x-axis, starting at 0 and accumulating until an x value of 1. So 0 to 1. This is a non-calculator exam question, so we have to be able to solve this definite integral without the aid of a calculator. And for the sake of discussion, I'm going to break this into two separate integrals. The second integral being easier to evaluate. The antiderivative of 2x is x squared, and we're going to evaluate that from 0 to 1. This antiderivative requires a little bit more work. It is a u substitution problem. So off to the side, I'm just going to make a note. U is equal to x squared. This means du over dx is 2x, or du over 2 equals x dx. And so when I rewrite the integral expression, x dx can be replaced with du over 2, and my e to the u is now this expression, and because my expression is in terms of u, I need to update my boundaries. So if I stick 0 in for x squared, I get 0 again, and if I stick 1 in for x squared, I get 1 again. Keep in mind, these are different in the sense that this is x equals 0 and this is u equals 0. If I take the antiderivative of this expression, constants go along for the ride, e to the u being evaluated from 0 to 1, plus, and we'll go ahead and simplify this out, 1 at the top, so 1 squared minus 0 squared. And then finally, we have to simplify this expression, 1/2 e to the 1 minus 1/2 e to the 0, and then plus this value totaling 1. E to the 0 is equal to 1, so we have 1/2 e minus 1/2 plus 1 is plus 1/2. So the total accumulated area is 1/2 e plus 1/2. This is Of course, the simplified answer, the previous step here, I had shown as a numeric answer, and so that would have received credit. The test question gets scored out of 3 points, so let's look at how those 3 points break down.
Your first of 3 points comes from having the correct integrand. So the integrand is that expression there. Your second point comes from finding the correct antiderivatives, and whether you write the antiderivatives in terms of u or in terms of x, finding those correct antiderivative is worth 1 point. And then finally, your last point comes from the answer. So 3 points in part A. Let's take a look at part B. All right, part B, write but do not evaluate an integral expression that gives the volume of the solid generated when r is rotated around the line y equals -2. So a rough sketch again, we have the region, and it's going to be rotated around the line y equals -2. Okay. So again, it's helpful to think of a representative rectangle, and when that rectangle rotates around the line, it's going to create the shape of a washer, if you want to think about it using the terms we use in class. That washer is a little difficult to draw in 3 dimensions, but our go-to formula for washers is pi r squared for the area of the outer circle, subtract pi little r squared for the area of the inner circle. And this gives you the surface area of the washer. If we multiply that by delta x, we get the volume of 1 washer. And if we then sum up all of the washers, pi big R squared minus pi little r squared, that are infinitely thin, this will give us the volume of revolution. And again, we're going from 0 to 1. So the general formula that we use for volumes of revolution is pi integral big R squared minus little r squared dx. And we have to identify what is our big radius and what is our little radius. So before I get into that, let's cut to a little clip that kind of animates this shape so that if you're having trouble picturing it on paper, you can maybe see it in the computer animation. All right, so what we see here is the blue curve represents xe to the x squared, and the brown curve represents the line y equals -2x. And then we have a rotation or an axis of revolution here at y equals -2. And the black line here represents kind of our representative rectangle. And what we're going to do is take the shaded blue region from 0 to 1 and spin it around the axis of revolution. So when we take that and we revolve it around, you can see the shape it makes here. And highlighted in black, we have a representative disk that is going to happen. And we can kind of sweep that disk back and forth, showing that as we move to the right, how that disk changes. The idea is we want to look at a single one of these disks. And we're going to take this disk, there we go, and talk about the outside radius, the big radius. And the big radius is going to be from the blue dot down to the axis of revolution. And the small radius is going to be from this brown dot to the axis of revolution. All right, so there's the visual of that, and let's return back to the paper and continue working on that. So as I said, the large radius is the distance between this point and the rotation line. So top minus bottom, our big R is going to be xe to the x squared minus -2. And our little r is going to be the distance between our
inner or lower function in the rotation line. So our inner circle has a radius of negative 2x minus negative 2. So now we have all of the pieces that we need to write the volume expression for this volume of revolution. Volume is pi from 0 to 1 integration, big R quantity squared, subtract little r quantity squared, stacked up along the x-axis, dx. And that's going to give us a total of 3 points for part B of this FRQ. 2 points come from the integrand, so having the integrand correctly, plus 1, probably docks a point for each error that is made. And then finally, the third point comes from the limits and the constant. So plus 1 there. All right, so part A and B are AB material, and part C is for Calculus BC students. So let's take a look at part C.
All right, part C says, write but do not evaluate an integral expression involving one or more integrals that gives the perimeter of R. So the perimeter of R would be this length plus this length plus this length. And if we do a little bit of analysis here, we might be able to extract some information so that we only need one integral. First off, this line occurs at 1, so the intersection point right here occurs at negative 2, sorry, 1 comma negative 2. Grab my whiteout. 1 comma negative 2. Likewise, this point here is going to occur when x is 1, and the y value, we can plug 1 into this equation and we get 1 times e to the first, so 1 comma e. And then we have the arc here. So we have 3 pieces. We have the diagonal line, the vertical line, and then the arc. And so let's start with the writing out in general. We have vertical plus diagonal plus arc. Those are our 3 lengths. So the vertical line is the distance from here to here. So we can subtract our y coordinates. Our vertical line is going to be e minus negative 2. And that's the length of this section. Our diagonal line, that's the hypotenuse of a right triangle, specifically a right triangle that is 2 units down and 1 unit across. So if we think about a triangle that's 2 by 1, by the Pythagorean theorem we can find that the third side is root 5. So our diagonal is root 5. And finally, this is a curve, so we can't use geometry, we need to use calculus. And the formula for arc length in calculus was 1 plus f prime of x squared dx. And this is going to be going from x equals 0 to x equals 1. So we're going to need to find f prime of x. Okay, so finding f prime of x, we're going to take the derivative of that function xe to the x squared. So this is a product, and it'll require the product rule, so f prime g plus g prime f. And this is a factorable expression, not necessary, but we can factor it, and that goes in the place of f prime of x. So our final expression for perimeter is the vertical line e plus 2 plus the diagonal line of root 5 plus the arc length of the arc, which is the integral 0 to 1 of 1 plus the derivative squared. So that answers part C, which is worth 3 points. The first point comes from, did you remember to take the derivative of f of x, or
more specifically xe to the x squared. That's worth 1 point. If you then lumped that into the arc length formula, that's going to get you your second point. And then your third point comes from, do you have the correct answer? Did you take the sum of these three values, the vertical line, the diagonal line, and the arc? Now, as an aside, it should be noted that the arc length formula we used was for functions in the xy plane. We can also do this using parametric if the expressions were in parametric form. And just a quick review, in parametric form, we have dx dt squared plus dy dt squared. So very similar to what we have here. In this sense, dx dt would be 1 squared is 1. And dy dt is that expression. Not exactly the same, but there's close similarities there. But this problem was not parametric, so that's extra intel. All right, be sure to smash that like button. Feel free to comment